Okay, so we're still in the first part of lesson 7. And what I want to do is talk about shear stresses on mutually perpendicular planes. Okay, so what we have here, what we're showing here, is this is a beam. Okay, this is a beam that's subjected to a shear force. And then we have a stress. So a shear stress that's resulting from the shear force. We're talking about this infinitesimal element A, B, C, D, which happens to be right at the edge of a free body diagram that we took from our beam. Okay, so we're considering this infinitesimal element. What we're trying to do is get to the point where we understand that when shear stresses exist on a plane, there must simultaneously exist shear stresses of equal intensity on a perpendicular plane. Is the point we're making here. There's really no problems in this section. We're just trying to make a point as to what shear stresses look like in an infinitesimal shear stress element. Okay, so if we look at this shear element here, okay, here's the tau 1 from our free body diagram. This was where the edge of the free body diagram was cut. This is our infinitesimal element. So we know that this element is in equilibrium. The whole beam is in equilibrium, so therefore this element is in equilibrium as well. The shear force on the right face, right here, has got to be balanced by an equal shear force at the left face. Equilibrium, sum of forces in every direction equals 0. So therefore, the vertical shear forces create a moment. Okay, so I've got a force in this direction coming from my free body diagram. I've got an equal force in this direction. These two forces make a couple. Okay, but again, this element is in equilibrium. It's not spinning. Okay, so therefore, a shear stress on a plane cannot exist alone. It induces an equal shear stress on the perpendicular plane. This state of stress is called pure shear. Only shear stresses exist on the element. Okay, so what we're looking at here is, here was our, we'll call it the shear force from our free body diagram. And we know that because the part's in equilibrium, we have an equal force over here. These two forces create a couple, which creates a moment about the center of this element. And we can't have that because we know that the body is in equilibrium, so therefore the element is in equilibrium. So therefore there's an equal couple here, tau 1 and tau 2, that balance the force out. So really, when we're talking about shear stresses in an infinitesimal element, here's what they look like. They have they're in both planes is what it is. So essentially it's a couple on both planes. So anytime we talk about shear elements, shear on an infinitesimal element, it's going to look just like this. Well, there's a chance that the shear could be in opposite directions. These two arrows point to each other. But we'll talk about that in a little bit. But this is what shear looks like on an infinitesimal stress element. It has to be balanced. A shear stress on a plane cannot exist alone. It induces an equal shear stress on the perpendicular plane. So get used to looking at shear stresses this way. Okay, so that really concludes what I wanted to cover in chapter 11. And then we'll go into chapter 17, which talks about combined stresses. The first topic I want to talk about in chapter 17 is biaxial bending. In biaxially bending, you have a beam, and the load direction causes bending about both axes, is essentially what we're talking about here. Okay, so in this particular case, my load P has components in this Y direction, and it has components in this X direction. So what's going to happen? We're going to have bending experienced on this beam in both directions. So using superposition, the stresses can be added algebraically. And how do we do that? We're going to go over this example in the problems here. And that's going to summarize our stresses. We're going to get mx over the section modulus at one point, we're going to get my over sy at the other direction, and then we're going to add those stresses together, making sure we get the signs properly, but we'll cover that. Okay, so the next section I want to talk about is combined axial and bending stresses. Okay, this is not a very, it's a common problem where you have a structural member that's subject to both axial and bending loads at the same time. That's depicted by this graph here. So what we have is we have a simply supported beam with a uniformly distributed load on it, and then we also have an axial load P here tending to pull the beam. Okay, so we have two sets of stresses. So the normal stresses is uniformly distributed across the section. That's what we're talking about here. So these are the normal stresses. They're just uniformly distributed. This is the same equation we've been using this whole semester. Sigma equals P over A. So that's a uniform distribution of the axial stresses. And then we have our bending stress. Okay, it's compression above the neutral axis. It's tension below the neutral axis. And then what we do by superposition is we can add the axial stresses to the bending stresses, and then we get essentially a new profile. In which case it kind of shifts the plane of zero stress from the neutral axis. It shifts it up to some other point is essentially what it does. And then we'll also going to be talking about this example in the problem section. Okay, there's going to be one more section in the lesson for lesson 7, and we're going to talk about combined stresses and more circles. Those videos should be out by Monday. Okay, thank you.